So, good evening, everyone. I hope I am audible to you all. So now today we are going to uh, start with the tutorial for the receiver functions computation. Apart from computation, we will also talk about H-kappa stacking, how to do the analysis using the stacking of the receiver functions to find the values of Moho depth and the BPY-BS ratio for the average crust structure. Before we go into the details of that, first I would like to show you some of the popular MATLAB Fortran boards that are available in the field of receiver functions to perform various tasks. So let me share my screen. So the first program, so the MATLAB test program that is actually written by I.W. Bailey from University of Southern California. Uh, so just you will have to type in like process RF MATLAB that then receiver function, and you will see a link will pop up. Just the first link that is on GitHub, and you can see there are some MATLAB tools available. So this basically these collection of the MATLAB codes are, I found it very important because it contains uh, all the steps clearly mentions and commented within the menu within the script, so that you can easily see what the steps in the scripts are doing. So there are various folders which are there, and uh, README files are also there within this MATLAB script. So you can see there is this deconvolution folder, depth mapping folder, example scripts. There is get info, in out, like with plotting, signal processing folder is also there. They have also provided some test data to on which you can apply all these scripts and to see how these scripts are working. And some inbuilt velocity models are also provided in order to depth migrate your receiver functions from time domain to depth domain. And you can also see there is some text written that it provides the information about these codes. And likewise, there is another code by Bob Burman, uh, which I think is very much popular among the students and also among the researchers. So Bob Burman is a scientist from St. Louis University, and these codes are very famous. Computer programs in seismology, CPS in short. Just click that link. I'm also pasting these links onto the chat box. Likewise, there's another link for the computer programs in seismology. So you can directly click on those links and to see what is there. Just to explain it a bit, you can see this computer programs in seismology is a lifelong work of Bob Burman, and he actually beautifully compiled everything at a single platform for the use of the seismology community. And in this, you can see There are several PDFs are available also. Uh, just to see the documentation, you have to just download PDF documentation here, and when you will click on it, you will see certain these documentations. You can see the first documentation is an overview of the synthetic seismogram computation. Another one is the surface waves, receiver functions, and crystal structure. Next one is the source inversion, and then it provides the overview about its own graphics that he developed for to be used in the programs that he actually developed. That is plot graphics, and then GSAC, that is also his own version of SAC. So it is generic seismic application coding, which is kind of similar to seismic analysis code, which you have done already in tutorial 5. These particular documentations also provide the mathematical background of any methodology or technique that involves the seismological computation, for example, for receiver function, dispersion curves, and also for moment tensor computation, source mechanism. So whatever thing you would like to do, it should be available on this in these particular documentation. Uh, just to actually give the kind of tutorials with data sets, we also put in some examples as a part of tutorials. And you can see these tutorials talks about basic seismology, synthetics, and then surface wave, again, receiver function, earth structure, sources, seismic data, and instrumentation. So for the receiver function part, you can see there are the tutorial for the determination of receiver function is available. There is another tutorial or advanced tutorial on receiver function, and also it talks about effect of the Moho gradient on receiver function RFTN and dispersion, effect of the shallow sediment in case some sedimentary layer is present in your subsurface, then how your receiver function will be affected. That also it explains within this tutorial. So if you just click on the first link, determination of receiver functions, so you can see step-wise procedure is written over here, and which I found very useful in the beginning for the students who would like to do their research in receiver functions, because it basically provides a hands-on experience how to compute, how to do the pre-processing steps on your seismograms in order to calculate, in order to do rotation and deconvolution, and then finally to compute the receiver function. So like it talks about what is the requirement of the program. You need to have your Bob Urban course installed in your Linux operating system. There are around, if I remember correctly, there are around 152 programs that need to be installed in order to successfully run all the utilities of the Bob Urban course. And they do also provide some example data sets. So when you so everything is there within this particular tarball file. So this is the zip version, as you have in Windows zip. Then likewise you have this tarball in Linux. So rftn.tg, if you will download it by clicking into it, then you will have to extract the folder out of it using this particular command, gunzip command, and then this particular folder will possibly be containing the scripts like I do EVT, I do event, I do rotation, and do RFTN, which is possibly be doing the removal of the instrument response, and then rotation, and then deconvolution finally. And it also talks about very sequentially like what you will have to do in order to run all these scripts, bash scripts. So these are the bash scripts. I do EBT, I do rote, and do RFTN. These are the scripts. And when you will download this tarball file and then unpack it, then you will find everything within that directory, including the seed file. Seed file is the seed file actually contains the data set. So it will be read by command rdseed. This is the rdseed command that is presented over here to extract the data out of this seed file, and then you can keep on doing whatever is written sequentially. So when you will do when you will perform all these steps together, then finally you will get these receiver functions completed for you. And then they have also provided some script to do back-assignment plot like this. This is the back-assignment plot of the receiver functions you can see. So in this, you can see this is the direct PV arrival. There is some current energy coming at around 4 seconds. Likewise, there is another current energy coming maybe around 14 seconds. And then the last negative energy that is not very much clearly visible to me at least. So this program can also be used. Likewise, there is another set of program or the course, MATLAB course, which has been made recently available. If some people who are working in seismology, they may know a code that is known as Split Lab. So the people from Split Lab, they have developed another scheme. So the Split Lab was the software to actually do the shear wave splitting to actually find out the deformation of the Earth's lithosphere and its movement. And then they have modified the same program in order to compute the receiver function. So the name of that particular program is Split RF Lab. And this is also available freely on GitHub. One of the most beneficial thing in seismology is that almost all softwares are really available. Okay, so you don't have to worry about the the expenses about software. You can download all the software freely without any problem. So either those are available through GitHub or maybe some individual websites are there to provide those data, to provide those software. So this is the Split RF Lab, which is a MATLAB GUI toolbox to calculate P-wave receiver functions, and also it performs H-cut by stacking. And this toolbox was modified by Split Lab and process RF MATLAB. So it also uses the process RF MATLAB and also the Split Lab together, and they have emerged out with a new software with the name Split RF Lab. So the installation procedure is also provided. Okay, here. So you can just follow it. All this is very simple to use. And likewise, there is another tool in seismology that is the oldest one, I will say, to compute the receiver functions. So, so like you just have to let me put this link also into the chat box. So this is for Split RF Lab. Next one is from Chuck Amon. He's also from St. Louis University. He's colleague of Bob Berman, who has also developed his course for the computation of receiver functions. So this is with the name of an overview of receiver function analysis. So here they have provided details about the receiver functions, the definition, and also the steps for typical receiver function analysis. Likewise, it also provides some information like how far the station does the receiver function sample the structure. You can just read through it. I think you should be able to understand what they are talking about. And then they are also saying about the data preparation. So for this code to work upon, you need to have your data in exact format, and then they do talk about the removal of the instrument response and gains, and then how to organize your set headers, that is also given there, and how to window your data. Likewise, some pre-processing steps. They also are providing the sec macro. I hope you know what sec macro uh, is used for. I think tutorial file does talk about that. And then they finally do say about the computation of receiver function. For the computation of receiver functions, uh, uh, they have sorry yes, in the source equalization only they have this code. So yes, yeah, this code. And also the okay I uh, so for synthetic for the transition of synthetic receiver function, they have a code with the names of with the name of rest KNT, response of a particular model. So either you incident a P wave energy or S wave energy. The response they have given like rest KNT. If you will type, then it will ask for the velocity model name. As soon as you will provide the velocity model, then uh, then it will ask like whether you are incidenting a P wave energy or S wave energy, so that the program would know what you would like to do, whether you would like to compute P wave receiver function or S wave receiver function. So in case if you are typing 1, that means you are likely to incident with the plane P wave energy, and the sampling interval that you need to mention, signal duration also you need to mention. Signal duration means the length of the receiver function that you would like to compute for, and then it will also ask you for entering the flow net. So that like typically for P wave, you generally put in 0.06, and then it will compute your receiver function. So this is also a very important program. It does also talk about inverting the receiver functions in a brief details, and also provides the uh, whole lot of theory about it. So so this is also a very important program. Let me put the link in here. Okay. So now that so these are the some of the important programs or software codes that are available. But apart from this, many other codes have been developed recently and in the meantime. So we will not be able to talk about everything. Let's talk about the one that we would like to see how the receiver functions are computed using the process RF MATLAB code. So, so like right now I am sitting in my office, and I am uh, uh, running Windows operating system into my desktop. So now I would like to access my computer, Linux computer, into my lab. That is just you may say 2 rooms away from my office. So for that purpose, I have this MOBA extern. So MOBA extern it actually provide the uh, provide the facility to remotely connect with your Linux system from your Windows machine. There are many other interfaces are available that you can use. I do use this mobile extern because I found it pretty handy to use it. So now I have opened this mobile extern. Now I would like to connect to SSH using X window, and there is one of my PhD students who has actually helped me to set up everything for the computation of video functions in MATLAB using process RF MATLAB code by IIT Dhanbad. So his name is Mukesh, and I am going to connect to his computer. The name of the computer is Earth, although uh, I would like to put the I would like to identify the system by its IP 172.16.52.16, and then it will ask for the password. If not, so basically it is not asking for the password because I recently logged into the system like half an hour ago to prepare all the files. Okay, so once the password is free, I think it didn't ask for the password for the next maybe 1 or 2 hours. I don't remember correctly. Okay, so there are so you already know. Now we are in the Linux system, so I can just list all the files, whatever are there in the current directory. So you can see that these are the number of files and folders that are available in my directory. I don't know which directory I am in. So to see that, I can type in the pwd command. So the path to working directory, that is /home/Mukesh. So that is my home directory, you may say. In my home directory, we have these number of files and everything. So now I have a folder that is already there with the name of GIAN in my desktop, in my home directory.
Sir, we are not able to see your screen. We just see your email.
Oh, I don't know. So let me share that. Now it should be visible.
Yes, sir.
Should I explain again?
Yeah, a little bit, maybe 3.
Okay. So let me close this mobile stuff. Okay, so as I told you, let me open the mobile stuff. So this is the mobile system which I just opened, and now I am starting a local terminal. So as I told you, my Linux system is just 2 rooms away from my office. So, and I'm going to logging into my PhD student system. The system's name. So in our lab we have several systems, several workstations, and some normal desktops. So all the for the kind of having some uh, so we have kept some names to all the systems like Earth and crust, mantle, core. Likewise, we have kept the name of all the systems. So now I am going to log into the system that is named as crust. Sorry, named as Earth. So SSH using SSH command using the X window. Then the PhD student's name is Mukesh at the rate the IP I will put in 172.16.52.16. So it will take me into the system, and then I will see where I am right now by just typing the pwd command, which you might know from your maybe first tutorial what the pwd command does. So this actually will print the working directory. So I am right now in my home directory /home/Mukesh. So if I would like to see the content of my current directory, I will just type in the ls command. So it will show me all the folders, all the files that are available in my home directory. And then, uh, so I have already everything set up for myself for this particular tutorial, and my folder is located in the desktop directory, and the name of the directory is GIAN within desktop. And then, so I have changed my directory to GIAN. You can see I will type in again pwd command. So now I am in /home/Mukesh, and within my home directory I went into the desktop directory, and within the desktop directory there is a folder with the name of GIAN. And then I would like to see the content of my GIAN folder. So this is the content of my GIAN folder. First folder is ANT, which is for ambient noise tomography, that we are going to do tomorrow. And there is another folder with the name RF. RF is the abbreviated form of receiver functions. So just to see what is there, I would like to open it, CDRF, and then I would again list the content of it. So basically, I have put in some data into my process RF method code in order to calculate receiver functions for those respective data sets. So, but before we go into see the data, first I would like to know what are those data, for which stations those data are for. So, so you can see there are two PDF files available in the RF folder. So one is the elevation map.pdf, another is the station_map.pdf. So I will just try to open these PDF, the station map, and see what is there, what is the location of the stations for which we are going to work upon to compute the receiver function. So I will, to open the PDF, I can either type FEH command or evils command. I actually prefer to use evils command because I am habitual of doing that. So I will use that station_map.pdf. So I think you know that if something is unique in a folder, you just type it first 2-3 letters and then just hit the tab command or tab key, then it will pop up the entire name by itself automatically. So I did so, and then I would like to run it in the background. So I will also put ampersand in front of it, and then I will hit enter to see the map. So the map has been generated. The PDF file has been created now. And you can see this is the map of Chota Nagpur Plateau and its surrounding areas. So you can see inside the map of Indian map is given, and its major cratonic regions are also identified within this inside figure of Indian map. So you can see there is Chota Nagpur Plateau, Singhbum Craton here, Bastar Craton, likewise Eastern Dhanbad Craton, Western Dhanbad Craton. Likewise, some major geological units of India are identified in this figure. And likewise, there is this at the very bottom. This is.
Sir, we don't see any figure.
Oh, I'm sorry. Okay.
Yes.
But is there any way to actually? I don't have to go back again, and whatever I will open, it will be visible to you. Because right now I am sharing windows, individual windows, I think. That might be the problem, that every time whenever I'm opening something, then you'll have to ask me, sir. So like, is there a way of doing that? Show all the windows. It is visible. The map is now visible to you.
No, sir, the map
No, sir.
disappeared.
Oh, again visible. Okay, that means now it should be. Okay.
Now it's visible, sir.
Yes. Okay. So you can see this is the map that I just opened up using the events command. And what I was saying in the inset, the Indian map is given that is identifying the major geological units of India by its abbreviations like CP, SC, DC, DBP. So all these abbreviations stands for like CP is for the Chotanagpur Plateau, SC is for Singhbum Craton, DC is the Buster Craton, and there is EGV, that is Eastern Ghat Belt, EDC, that is for Eastern Ghat Craton, likewise. And our SPB area is marked by this red rectangular block, which is actually denoting the Chotanagpur Plateau, and which has been expanded in this map. So this is the region of Chotanagpur Plateau and its adjacent areas. So you can see several faults are also superimposed on this map. So these, so like there is this GKGF fault, which means this is a Germanic Kandagoshi fault, and there is this PF, this is Pingla fault. Likewise, Saithya Mahabani fault, and some districts are also marked on this map, like Sirsa district, Purnia, Katihar, Raiganj, Rajouri, Jhajjar, Baka, and Devghar. And there are some stations are also plotted on this map. These are actually uh, marked by these red triangles. So these red triangles are denoting the location of the stations with their station codes. So this is for Kuti. KNTI is the station code for Kuti. And this is for PTWR. This is for Pitabar. This is for Bokaro, BOKR. This is ISM. And this is SBG. I think many people do know about that, that ISM also has a permanent seismic stations, which means we do have an observatory within the campus premises of Indian Institute of Mines, IIT Dhanbad. And this observatory continuously record the data 24/7 from all across the globe. Whenever any earthquake happens, it does record the data. Even the earthquake is happening in Japan or maybe Australia or somewhere else, it will be recorded in the observatory of IIT ISM. Likewise, there are stations which were deployed by National Center for Seismology. So this is like BOKR film from National Center for Seismology. This PTWR, this is Petrobar, that is the station which was installed by our research group at IIT ISM. That has been running from the last 2 years, since from I would say around mid of 2019, more than 2 years of data it has now. And this is Kuti, that is again the seismic station deployed by National Center for Seismology, and this is the Sahibganj station. So this is the station map. We do also have two more stations recently deployed in the region of Chotanagpur Plateau by our research group. One is in Nirsa, which is basically 40 kilometers away from Dhanbad, and another station that we have installed is located in Giridih area. So and we are planning to install a station in Devghar pretty soon. So our own network from our research group will be having around 5-6 stations in the area of Chotanagpur Plateau. So basically, if I will talk about, if I will show you other stations in the region of Chotanagpur Plateau. One second. Yeah. Let me share this screen. now. So this is the plot. So these balloons, are you able to see the map with balloons? Yes, I think. Okay, so you can see this is the station. So these are the stations which are having the plan for the future development also. Like you can see, there are stations with the green balloons. There are stations with the blue balloons. They are stationed with orange balloons as well. So what I am doing, I am trying to show you here is that the stations which are identified by orange balloons are from National Center for Seismology, New Delhi, and the blue balloon stations are deployed by our research group, and the green ones are the data that was collected by an experiment from our National Geophysical Research Institute. So we are planning to actually image the entire lithosphere of the Chotanagpur Plateau using the seismic stations data from this entire network of stations. Uh, for the purpose of today's tutorial, we are going to see uh, the receiver functions for mainly two stations. One is for Bokaro, and another one is for ISM station. So let me show you so this is the ISM station here, and this is the Bokaro station here that I am going to process the data for. And now let's go into the processing part. So, so there are basically two folders in my current directory. One is the Bob Urban folder, and the one is the process RF MATLAB. So because our purpose is to compute the receiver function using the process RF MATLAB code, then I will just go into that directory CD process RF MATLAB and then list what is there. So you can see actually there is a folder name again there, process RF MATLAB underscore master. I will go into that, and you can see within that there are certain number of folders and files. And now to basically run all these scripts and files, let's first look at what is there in each of these directories. Okay, so I can just type ls star to see what is there in a one go. Okay, so when I typed in ls space star, then it is showing the content of each of the folder to me. So within deconvolution, there are certain number of MATLAB files you can see. So one is the Gaussian filter.m, make rf dem.m, make rf iterdecon underscore langston.m, make rf iterative deconvolution.m. Likewise, many other files are there. Likewise, so you can see, as I told you in my today's lecture in the morning, that deconvolution can be performed by in frequency domain as well as in time domain. Both of the scripts are available. MATLAB scripts are available within the deconvolution folder. So this one is for the iterative deconvolution, and this one make RF water underscore amount is for water level deconvolution, that is in frequency domain. Likewise, there is another folder, depth mapping folder, within which we have several other codes. One of the one which we are interested in is the HK stacking code. So HK stacking code is there. There are several versions are also available. So we'll have to see which version is which one is the correct one. And then there is a folder with the name example scripts. Okay, and example scripts, and within that there is a folder with the name example data. So within this folder there are some seismograms, example seismogram, for which the code will run and get the receiver functions computed for you. And then there is some get info folder. There is within which you have a script with the name estimate snr.f, and then there is some get the absolute value of the maximum amplitude, and there is arrival time calculation code of the different phases, and slowness calculation script is also available to calculate the slowness. Likewise, some plotting folder is there. Likewise, signal processing folder is there. The signal processing folder within which there are several important functions are available uh, uh, within the signal processing folder. So likewise, there is some test scripts. Okay, so let's go and see what is there as a data. So like I will go into this example script folder, and then we'll go into the example data, and then I'll see what is there within seismogram folder. Sorry. And then go to the event, and then so the data I have kept it for the year 2017 for the station ISM to compute the receiver functions. So let's see how the seismogram looks like for the 2017 year of IIT ISM. And so to look at those, so let me tell you, these files are SEC files. So we can open these files using the SEC software. Just type in the SEC command here, and then it will open the SEC interface, and then you can read those files. Let's read the vertical component first, because if you look at the naming conventions, so each earthquake has 3 files, because each earthquake has 3 channels that are recorded in the instrument. So like the last 3 letters are representing the component BH. B is for the broadband, E is for the east-west. B again, so this one is for the broadband, B, and N is for the north-south. This is B is for the broadband, and Z is for the vertical component. So the earthquake that has happened on 2017 in the first month and the 10th day and 6th hour, 16 minutes and 19 seconds. Okay, so this is how you can see the nomenclature of files are done, so that you can easily identify the time when this earthquake has happened. So this earthquake has been recorded at ISM station, and this file is associated with the east-west component, and the earthquake has been recorded on the broadband seismogram. B is for the broadband. If suppose instead of B you have S, that means it has been recorded at the short period instrument. And likewise, if you have L, that means long period instrument. So this is for broadband. Okay, broadband data. That means it is covering both short period and the long period. So it can record the very high, like the entire broadband of the data, all the frequencies of the data, almost all. Okay, and then this is the ISM station, and this is the year, this is the day, this is the hour, this is this is year, this is month, this is day, this is hour, and this is minute, and this is second. So likewise, if you want to see, let me go back a bit. If you want to see how many earthquakes are there within this folder for ISM station for the year 2017, then I can just type ls star, just count the number of files. So it will say like 30 files are there. That means 30 divided by 3, because each earthquake has 3 files. So 30 divided by 3, that means 10 earthquake data is there. And to see how these seismograms look like, then I will just go into the SEC software by just typing sec and then hit enter, and then the sec will open up. Then I will just type R command and the name of the file. So I would like to see, I would like to read, let's suppose I would like to read one by one the files. So let's suppose the first file I am reading in. So then I will type, I will hit enter, and then I would like to list headers of this sec file. Then I will do LH. So it will show me basically what are the headers in there within for this particular sec file. Dheeraj, please mute yourself. Yes, okay. Thank you. So it will list all the headers within this, and you can see this first header is basically representing the number of sample points. That means the number of samples that are actually taken to record the entire seismograph. So this is like around 20 to 1900. And the beginning time of the seismogram is around 0, ending time is around 2218, and it is a time series, it is a evenly distributed data, and delta is for the sample interval, that is 0.01, and likewise the minimum amplitude on the seismogram is minus 5.8 into 10 to the power 4. Maximum amplitude on the seismogram is 2.62 into 10 to the power 4. What is the mean amplitude of all the data recorded is minus 1.08 into 10 to the power 8, 10 to the power 4. And the P wave has been marked on the seismogram already, that is arriving at around 243.2 seconds, and S wave is arriving at around 557.13 seconds. And when the earthquake happened, what is the time, what is the station name. Likewise, you will see what is the distance from the station what is the distance of the earthquake from the station. The distance of this earthquake is 4.4 into 10 to the power 3, which means 4,435 kilometers away from the station ISN. So you can see like the earthquake is happening around 4.5 thousand kilometers away from the ISN station, but it still has been recorded at our observatory. And the back azimuth of the seismic station of the event and seismic station is 1.13 to 10 power 2, and the distance in degrees is 3.98 into 10 to the power 1. That is 39 degrees away from the seismic station ISM. And likewise, many other fold of headers are there. The magnitude of the earthquake is 6.9. And if I would like to plot, then just I will hit P and then enter. Then it will basically open a graphics window in SAC, and you can see this particular seismogram looks like this. Okay, so on this
Seismogram.
Hello, yes.
So we cannot see the seismogram.
Oh, I'm sorry. I think now it should be visible.
Yes, sir, visible.
Yeah. So this is the seismogram that I just opened up, and by hitting the P command, and you can see the P wave marker is already there. So this is P phase that is coming. So like before the P wave, and there is some noise, and as soon as the P wave arrives, the amplitudes are getting higher, and then S wave comes in, and then maybe some surface wave energy part is over here. And you can see on the x-axis the times are there, on the y-axis amplitudes are there. And on the graphics window, the station code ISM is written. This is a vertical component data, VHZ, broadband, and the vertical component jet, and the timing and the date of the earthquake is also mentioned over here. Likewise, let's close this window and let's go back again.
Sir, one question about this plot.
Yes.
So what is the unit of the y-axis and the x-axis?
Y-axis probably the y-axis probably in counts, and the x-axis in seconds.
Y-axis you said it what?
In counts.
Pounds? Okay. Thank you.
Okay. Now let's move back to the MOVX term. Okay. So is it visible whatever I have typed right now? Is it visible?
Yes, sir.
Okay. Now let's look at all the components of this particular aspect together. So, okay, and then I will type P1 command to see here. We can see all the components together and different tiles are plotted. So the top one is the east-west component, the middle one is the north-south component, and the bottommost one is the vertical component. And in this one, you can see all the energies on all the channels simultaneously together. And because sometimes what happens, like you want to quick P waveform and S waveform using the commands that were told to you earlier while discussing about the SEC tutorial. So the PPK command, APK command, if you will remember. So all the components you will have to open maybe sometimes together to actually correlate between that. Okay, this is why correlate and uh, 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 to efficiently identify the P wave energy and the S wave energy. So that is why you can type in the P1 command and see where is the P wave energy coming and where is the S wave energy coming. Okay, so and if you want to plot all these seismograms together on top of each other, you can just type P2 command. Okay, so this is how I think. So this is how you can plot. Now let's move on to the MOVX term back again. Okay. Now that likewise you can also plot other seismograms too. So there are overall 10 events. There are overall 10 events. So yeah. So now let's quit it, and then let's go back. And there is this script. This is script 01 process trfns.m. Let's open it. What is there? I can use vi command to open. This is the editor. There are several kind of editors like Emacs also can be used, vi editor can be used, and also gedit can be used. I prefer to use vi editor because it has several important commands within it that I can type into actually or promptly edit the text within a file. Gedit although is good, it's very easy to use gedit, but it is not as much as powerful as of the vi command. So I will suggest all of you, if you are working in the field of seismology, or you have, or even if you are in the different fields or and have a lot of text editing, uh, then you may use the VI editor for doing so. So let's open this particular MATLAB script. VI script 01. So now we can read this particular file, and you can see there are some comments written within it, and it says about the author's name, GIAN W. This is the GIAN W. and it was written like in 2012, you can see it is almost 10 years ago. So on Monday, June 18, 2012. So this is actually where I was doing my PhD. Okay. So the function, you can see there is this is plot written. This is actually argument. If this is true, that means it will plot all the steps one by one to actually interactively show you all the processing steps. And if you will keep it false, then it will directly take you to compute the receiver function. And these are some parameters that are set before going actually to the script. So like this op dot means is one. This is the depth of the earthquake, minimum depth of the earthquake, maximum depth of the earthquake. So for the receiver function computation, you need to basically set some parameters. Like you will have to tell the program that like what should be the minimum and the maximum depth of the seismogram for which you would like to compute the receiver function. If suppose your earthquake event is not lying within that particular depth range, then it will be automatically rejected, and then it will move on to the next event to compute the receiver function. And then this is the op dot del min. This is the distance, the minimum distance, that is 30 degree. Maximum distance is 95 degree. And as I told you, to have the plane wave approximations, you must have to have the distance more than 30 degrees. Only if you will have the distance more than 30 degrees, then you may be able to sample the upper mantle or the lower mantle of the subsurface of the earth. So that which means you can actually sample the deeper structure as well. Likewise, if you this is the phase name, that is the incident period energy, and that is kept as T, and this is T before and T after. This is 30. That means the time before to cut and time after P to cut. So like wherever the P of energy is starting to come, and then around that P of energy, you would like to make a window in order to actually do your processing steps or the further processing steps that you would like to do. So this is the tapering that you would like to perform to smoothen the end of the seismogram. That is the 5% taper that they are using. Likewise, the filtering, low pass filter is 2 Hz, high pass filter is 0.02 Hz. And likewise, several other parameters like magnitude, the minimum magnitude is 5, maximum magnitude is 8. So that means the earthquake's magnitude within this range will only be eligible to go further for the computation of the receiver function. And finally, the receiver functions that you will see will be having the time window from -10 to 90, and where the 0 will be the arrival of the direct beam of energy. And next, there is some commands that they have put in for identifying the directories of the event data. So, like for example, as I told you, as I had shown you previously, that our data is within the example data file folder, and within which there is another folder that is with the name of seismograms. And then it will went on to see whether all the 3 components are available or not with the extension BHG, BHN, and BHZ. Likewise, if it is not available, then it will reject the event and will move further to the next event. Likewise, after they have identified all the components within all the fact files, it will try to get the information about the arrival times by using this function get times, and then it will check the units for the depth also. Then finally it will do rotation of the seismogram from vertical north south east west component to vertical radial and transverse component, and the function that is available for doing so is process ENZ size. This is the function. And Then finally, after the rotation, they will perform the water level deconvolution. There is this script process RF water, and then there is another script process RF return. Okay, so this is how this particular MATLAB script works. Let's run this script to see what it does.
Sir, one question.
Yes, yes.
So these codes are specific to Linux, or are these codes related to Python or some other software, or this is Linux code?
These are the MATLAB codes. Okay, if you have MATLAB running, either it can be on Linux also, it can be on Windows also. It can run, these codes can readily be run on both the operating systems.
Okay, sir. Thank you.
Okay, now let's open the MATLAB. It will take some time to open. So now it has opened. Let me share my screen. So this is my MATLAB command window here, and let me So before you actually run this any code within process RF MATLAB, there is this particular code, this process RF MATLAB, this one process RF MATLAB underscore startup.m. So this code basically add all the paths of all the folders available in process RF MATLAB to the working directory. So before you run anything, you first need to have run this MATLAB script. So I will run it. I will just drag it to the command window like this, and it will add all the parts. Now I am ready to run any script that I would like to run. Now let's go into the example scripts folder. Okay, and then there is this script 01A underscore process PRFNS. I will just drag it to here, and it will start to run. So now that it is ready to run, so first figure that it has generated is for it is actually showing me the seismogram. So this is the seismogram of the first event on which it is trying to do the pre-processing step. So you can see the top one is the east-west component, middle one is the north component, and Z is the vertical component. Now I will hit enter, and in order to continue. So now you can see it will actually shade the arrival time of the P wave by the red color. This is basically showing that we are windowing our data.
Sir, seismogram is not visible.
I cannot do this. Is it visible now?
Yes, sir.
Okay. Now this red shaded part is basically telling us we are windowing our seismogram around P wave energy, and the time for this adjustment is lying in between 213.19
Sir,
seconds.
excuse me, sir. Can you
Okay.
explain I mean, before from starting step, like process RF is there? how
Yeah.
this window came in the time we missed.
Yes, yes, yes. Let me go back again. Then. I will run again. So this is let's run it again. Okay. So now what I am going to do, I am going to run this script. I hope it is visible to you. A script 01A underscore process prfns.dat. Okay. I am going to run this script. Just typing the name of this script. Okay. So I am just typing this script and then hitting enter. So as soon as I will hit enter, then it will actually open this figure window. Let me share the screen for the figure. Yeah. So you can see the figure has opened up, and there you can see three components for which I would like to compute the receive function. So in this three components, this is the PV arrival time. This is the PV energy that is coming. Let's see. Yes. Are you able to see my cursor? I hope so. Okay. So
Yes, yes, sir.
so this is the P wave energy that is coming over here. So because I would like to compute P wave receive function, so I will make a window around P wave arrival time. The window would essentially be having the length as I have mentioned in my script already. So 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 I will hit enter onto my command window, and you will see that another figure will pop up, this one, where the windowed part has been shown in red color. Okay, so the windows adjust time is in between 230 seconds to around 423 seconds. Okay, so this is the this is the starting time of the window, and then you have this period arrival time, and then after period arrival time I have selected a longer window, longer length, because after the period arrival time you will have the multiples, right? So because P2S converted phases will arrive later after the direct period arrival. So I will have to select the larger length of the window after the PV arrival time, and before PV arrival time I am taking the smaller window because it is not very much useful to us. Okay, so then I will hit enter again, and what it will do, it will basically remove I think it will remove the direct current or DC offset. It will remove so that it can uh, remove the fluctuations from the time series. Okay, so the removing DC is a important step that needs to be done on the seismogram. So you can see the comparison between the seismogram before. So this is now the windowed part that has been actually zoomed out for you now. So you can see this is not the entire seismogram now we are looking at. This is the windowed part. Okay, this is the P wave, and this is the 213 second starting time. Here is the 423. This is the windowed part that has been shown in the red color in the previous figure. Okay, so now after removing the DC, the comparison has been given here. You can see the red color is representing the the windowed seismogram after the DC offset, and the black one is showing before the DC offset, before the removal of the DC offset. And then again I will hit enter, then it will taper the seismogram. So you can see this black part at the end of the seismogram. So basically it will smoothen the end part of the seismogram, and then So we are using 5% of the data. Now I am going to do bandpass filtering on the seismogram. So the bandpass filtering is being done between 0.02 hertz to 2 hertz. So that is the normal range of the frequencies that I would like to contain in my receiver functions. So you can see here the comparison after the bandpass filtering and before the bandpass filtering is given. So the black one is the seismogram has been overlapped over to the red one. The red one is after the bandpass filtering, and the black one is the before the bandpass filtering. So these are all the key processing steps before I am actually running on to the rotation of the seismogram. Okay, so these three processing steps before the rotation. Then we will go on to the rotation. Then we will go after that. After the rotation, we will go on to the deconvolution. So now let's move on. And now you can see I have removed DC. I have done the tapering. I have now also resampled my data from 0.01 sample interval to 0.1 seconds. And now I am doing the rotation. Okay, I have done the rotation and then also done the deconvolution. Okay, both the things have been done together. This is the final product of receiver functions computed both from the water level deconvolution and also from the iterative deconvolution. Okay, so the blue one is the receiver function computed using the frequency domain deconvolution, that is the water level deconvolution, and the another one, that is the red one, is from the iterative time domain deconvolution. So you can see, you can compare both the receiver functions together. You can see like both the receiver functions are pretty comparable to each other. So by plotting this figure, I do not need to say anything about which one is more suitable or which one is more less suitable. Both the techniques are equally important and equally producing good results. So so we cannot say anything about like which one is better. Both the techniques are producing almost similar results. So now, so this is how you can compute the receiver function. Now I have shown you the step-by-step procedure. Let's move on to the next event to see how can we do these steps on the next event. Okay, so let's see the seismogram. So this is my seismogram for the next event, and then I am hitting enter and adjusting my time into around 3 hours. So the adjust time is like 95 seconds to 305 seconds. Now I am removing the DC offset, and then I am tapering. 5% taper is being applied, and then I am bandpass filtering between 0.02 hertz to 2 hertz, and then finally I have, this is my final, this is my the windowed seismogram around pre-arrival after doing the pre-processing steps. Now I am rotating and deconvolving the vertical component from the radial component, and after the deconvolution, the receiver function may be looking like this from both water level and the iterative time domain deconvolution. Likewise, I can compute my receiver function for the next event and the next event. So this is the next event, and I am hitting enter again to adjust the time into around 3-wave arrival between 333 seconds to 543 seconds, and then I am again hitting enter to remove the DC offset, and then again hitting enter to actually tapering the seismogram, and then I am putting bandpass filtering to remove unwanted signals from the data, that is from 0.02 hertz to 2 hertz. And then I am performing the rotation and deconvolution together to actually form the receiver function. Likewise, you can do the same thing for the many event together. So just for the sake of the purpose to show all the steps step by step to you, I have actually used the true command as an argument for this function. If I don't want to see all the steps because I know what is happening, then it will compute all the residual function all together for all the events. If I will just hit the command, if I will just type the MATLAB script name in bracket false. So let me share my window, MATLAB window again to you. So now, if I will just type in script 01, this is the same script that I was using just a while ago, and then in bracket I will just type false, and it will do everything automatically without showing me each step one by one. It will compute all the receiver functions for all the events now, and then I can see the product. There is a folder with the name PRFNF. Okay, I can just show you. Okay, so I will go to this PRFNF folder. All the receiver functions are kept in that folder, PRFNF. And this is the folder in the folder within the folder for iterative time domain. So it is actually forming two different folders for the receiver functions that are computed from water level deconvolution, and the another folder that is computed that has the receiver function computed from iterative time domain deconvolution. So I am right now a little bit confused what folder has been created right now. So just look at the formation, the time at which these folders are created. So all the folders were created long time ago, like May 11. Today is May 16. So I think this is not the folder that we are searching for. Let me see within the code where it is keeping the data. Okay. So there is this folder ISM, the ISM data underscore all. So you can see I have already computed receiver functions for many years of data in this particular folder. You can see. Okay, so you can see the receiver functions starting from the year 2007 to around 2017 are there. Around 10 years of receiver functions are available in this folder that I have already computed. Actually, sorry, I did not compute it, Mukesh has computed. Okay, so Mukesh has already computed this 10 years of receiver functions or ISM station. And let's look at these individual receiver functions to have a glimpse of how these receiver functions are looking like. Let's read all the data all together, in fact, and then plot one by one. Let me share the window. So you can see this is the receiver function, first receiver function, and this is another receiver function for another event. This is another receiver function for the next event. This is another event. Likewise, many receiver functions are there. As I told you in my lecture today, that we need to compute receiver functions for the many events and then stack them all together to get some useful information out of it. Individual receiver function may not tell you many things about the subsurface structure. In order to image accurately the subsurface structure, you will have to stack, or you may have to use some kind of technique to resurrect the information out of it. So these are all the receiver functions. Many receiver functions are there. Okay, if in order to plot all these receiver functions, so I have a script to plot all the receiver functions as a .ps file. So there is this script that is available there. So is it visible? I think so. Okay, so this is here. This is the script that I'm going to use. I won't give you much detail of it. Just I will run it to see how my receiver functions all together in single gather are looking like, and to actually identify the flow and phases which might be available on my receiver functions for ISM station data. So let's run it. And yeah, so when I ran it, so it gave me this figure, and you can see on the x-axis the back azimuth values are given, and on the y-axis the time are given. And this is all, these are all the receiver functions that we have computed for ISM station for the years in between 2007 to 2017. And you can see these all receiver functions are very beautiful. And there are some current energy can easily be identified on this gather of receiver functions. So this one this might be the intercrustal phase. This might be the PS converted phase from MOHO. This might be the PPPS phase from MOHO again. And there is some negative energy coming over here somewhere, like at around 21 seconds. That may be for the PPSS phase or PSPS phase. So do you have any questions so far? Okay. Okay. Likewise, if you would like to actually uh, mm, plot your gather of receiver function with respect to array parameter, there is another script I have with me. So the script is like this. This is another script that plots your receiver functions with respect to array parameter, and it does look something like this. And if I will run this script, I'm sorry. Okay, now I am running this script. And I see, so after running this script, my receiver functions gathers are plotted with respect to the parameter. On the x-axis, the parameters are provided. On the y-axis, the times are provided. So you can see with respect to the parameters, your gather will look something like this. And now, so likewise, we we have receiver functions already computed for the seismic station BOKR, that is Bokaro. So these are the receiver functions that we have already computed for seismic station Bokaro. And if you would like to see how the receiver functions look like for Bokaro, it is like this. So this is the receiver function for seismic station BOKR Bokaro for the event that happened on September 11 in 2008. Likewise, another receiver function may look something like this. This is the next one, and this is another one, and this is this one. Likewise, there are many events for which we have computed receiver functions for seismic station Bokaro. And if you would like to see let me run the script for plotting the gather of these receiver functions with respect to back every month. For that purpose, so I will just run the script. And after running this script, your gather would look something like this. You can see it's also we are producing a very good gather of receiver function, and you can easily see the current energy that might be that is there. So like you can see there is this current page, this is here. So these current phases actually tells you about there is something within the subsurface which because of which all these current phases are being produced. So you need to interpret these phases either using some kind of methodology like phase tracking or maybe inverted technique or forward modeling or maybe common method point extract technique that can also be performed in order to identify uh, 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 geological features which are responsible for generating these current phases. So gathers are pretty much important because so only after looking at these gathers you can basically identify okay this phase is coming currently and consistently in all the receiver functions. So that means it confirms the presence of some geological structure within the subsurface of the earth. So likewise, you can also plot receiver function for BOKR using with respect to array parameter. So for the purpose, I will just type in that I will just run that code in. So with respect to array parameter, it does look something like this. Okay. Okay, guys, I now would like to ask you all. So this is about the computation of receiver functions. If you want to do it by yourself, you can download the code. I have sent you the link. And after downloading the code, you may want to run it. You can run it. You just have to have MATLAB installed into your system, and then you can pretty much good to go. So you can you can download the code, run it into your system. Now I am sending you a PDF on your email for a paper that is from Ju and Kanamori. for that, because next thing that we would like to do is to I want to show you edge compass stacking. Okay, how to perform edge compass stacking. That I would like to show you. So for that, before I would do so, I would like you to do, I would like you all to go through the paper from GIAN Kanamori. Okay, so let me send that paper to you all on your in your inbox. So this paper, uh, yes, yeah. So this is the paper that I have just sent to you all. In please check your inbox and open the paper up and start reading this paper. At least try to have some glimpses of the paper before we actually start to do edge compass tagging. So I am taking around 10 or 10 minutes break right now. In between, if possible, please read the paper. So guys, you might have had glimpses of the paper. I know it is almost not possible to read the entire paper in 10 minutes. So just to so if you look at this paper, it is the one of the uh, it is the first paper uh, uh, which was actually published in 2000, providing the theory behind the exercise taking method using some synthetic seismogram as well as using some real-time data. So sorry, of some real data. So if you look at this paper, uh, in the introduction part, they talk about Moho discontinuity, which actually separates the Earth crust from the underlying matter, and they have performed the exercise tracking for the area of Southern California on uh, several stations. So they put the theoretical basis behind this technique and talked about what is exercise tracking and also done the exercise tracking using some synthetic data. So you can see this is the gather for P2S ratio functions, and these are all the synthetic ratio functions that they have completed. And using the inbuilt velocity model, like the standard Southern California velocity model. And the velocity model looks something like this, for which they have computed the synthetic ratio functions. And then using these synthetic ratio functions, after applying the exercise taking, they try to estimate the Moho thickness and the mid-to-IBS ratio. So, which was this is the exercise taking plot. On the x-axis, you have the variations in H, that is Moho depth, and on the y-axis, you have variations in the kappa value, the variation in BPY-BS ratios. So they have shown this formula here. You can get that we already have seen in my morning lecture, which is W1 RT1 plus W2 RT2 minus W3 RT3. And this RT1 basically denotes the amplitude of P2S converted phase. RT2 denotes the amplitude of PPES phase, and RT3 denotes the amplitude of PSPS and PPSS phase. And weights for the respective phases are such that they should sum up to 1. And because the P2S converted phase are most clear in the ratio function gathers, if you compare it with the PPPS phase, and PPPS phase is clearer than the PPSS phase. So the weights are given in the decreasing order, which means W1 is greater than W2 and W2 is greater than W3. And this is how you should find out the uncertainties in your results of H and kappa values. This sigma is denoting the variance of SHK. And for this purpose, you will have to perform the finite difference and then expand that using the Taylor series. Then they are talking about the Southern California region and its geology and the data that they are using. So they are saying that the waveforms of around 416 teleseismic earthquakes recorded by these stations are retrieved from data archives at the Southern California Earthquake Center and the Incorporated Research Institution for Seismology. Right now, so they have almost used around 45 broadband stations, for which they have used around 416 teleseismic earthquakes. And these earthquakes are basically lying in the epicenter distance range of 30 degree to 95 degree. And data was collected in between years 1993 to 1999. And the magnitude of these earthquakes was more than 5.5. And they have windowed their seismograms around P-wave onset for a time window length of around 150 seconds. and then they actually computed their receiver functions and then assigned the weights to the different phases. For the PS, they have assigned 0.7, for PPPS 0.2, for the PSPS and PPSS is 0.1. So this is the results they have compiled into the table format. So you can see the first column is for the station code, second one is the latitude, longitude of the station, elevation of the station in the fourth column. Likewise, the arrival time of the PS phase is in this column, in this column, and the mode thickness in the second last column, and VPIVS ratio in the last column. And associated uncertainties in H and kappa values are also given there. So, like if you will talk about this one, so this H value for the BAR station is 34.2, which is having the uncertainties about 1.6, which means the value of H may vary in between 34.2 minus 1.6 to 34.2 plus 1.6. Likewise, V2IVS ratios are given in the last column. So this is a large table for consisting of results of around 45 stations, and then they have shown their some of the diagrams of ratio function gathers with respect to their parameter, and this is the expect plot wherever they are getting the highest amplitude of the highest value of FHK, that means the bullseye. That the associated values of corresponding values of the K and H are the values of the core thickness and the radius ratio. So then they have plotted their results on the map of Southern California, and then they are showing the variations of the mode thickness. You can see this is the color coded map of Mohit Mohit depth variations of Southern California that they have produced using the HFI technique. So this is the paper that was published in 2000, and what I would like to do now, I am actually about to finish this tutorial now. If you have any question, please go ahead. We will do HFI stacking in the next tutorial along with seismic profile, along with ambient noise profile. Do you have any questions so far? So I assume there is no question. So that is all from my side for today for the tutorial. Tomorrow at 7:30 a.m. we'll meet again for the last lecture, where uh, I will be starting with seismic interferometry, and we will be talking about passive force interferometry. Thank you so much.
Thank you, sir.